A gamma-ray burst can outshine all the stars in the sky. It's a single flash, and it has the power to erase life across a galaxy in seconds. This is the science of it. These explosions that could end a universe, and the odds we face where they're born, whether Earth has ever been in the line of fire, and what it means. For life to exist in a cosmos that's this dangerous, the brightest thing you've ever seen like a camera flash, then imagine giving that flash the energy of 1 trillion suns. Compress all that into a few seconds and set it off across the universe. That's a gamma-ray burst. For just a moment, it outshines entire galaxies. It becomes the most luminous thing in the cosmos since the Big Bang. The numbers don't make sense. In those few seconds, it releases more energy than our sun will over its whole 10 billion-year life. That scale of power, it feels less like astronomy and more like mythology. And for a long time, that's what they were, a myth, a ghost in the data. Their discovery story is almost as strange. In the 1960s, during the Cold War, the U.S. launched satellites called Vela. Their only job was to watch for the gamma-ray signature of nuclear weapons tests in the atmosphere, a treaty violation. But what they found was something else. They started picking up brief, intense gamma-ray flashes, and these flashes weren't from Earth, they were from deep space. Random points in the sky, no pattern, no warning. That data was classified for decades, a military secret. Even after it was declassified, scientists were baffled. What could produce such a catastrophic, short-lived spike of the universe's most energetic light? The mystery was so deep, some researchers wondered if the signals were real or just a detector glitch. The truth was stranger. We'd accidentally built a sentinel that wasn't watching for the end of a world, but for the end of stars. We opened a new window on the cosmos, and the first thing we saw was a scream of pure energy from the void. That mystery, what could create such violence, leads us straight to where these titans are born. The answer was in a star's death, not a quiet fade, but a total collapse. A star much bigger than our sun, dozens of times more massive. It burns for millions of years, fusing elements, fighting its own gravity. It builds layers like an onion with iron at the center. And iron is the end. It takes energy to fuse, it doesn't release it, so the star's furnace just stops. The outward pressure is gone, and all that weight held back for so long, it just falls. The core collapses in under a second. It doesn't stop at a neutron star. It keeps going, crushing down to a point, infinite density, a new black hole. But that's not the end. The star's outer layers, they're falling in, almost at light speed. They don't just disappear, they swirl around the black hole, a superheated whirlpool. An accretion disk, matter there is torn apart, heated to billions of degrees, and from the poles of this chaos, physics does something. It focuses the energy. It channels it. Two narrow beams shoot out, particles and radiation, punching through the collapsing star like cosmic blowtorches. These jets, moving at 99.9% light speed, that's the gamma-ray burst. The star's final scream. If one of those beams is aimed right at Earth, we see a long gamma-ray burst, a flash that lasts from 2 seconds to minutes. The explosion that makes it is so violent it has its own name, a hypernova. It outshines a supernova by 100 times. It's the biggest explosion a single star can make. And what it leaves behind is permanent, a black hole, and the scattered, enriched remains of a giant star, seeding the future with the heavy elements from its death. There's another way the universe makes a gamma-ray burst, a second kind of cataclysm on a completely different timescale. If the collapse of a giant star is a long, final act, this other origin is more like a sudden crash in the dark. It doesn't start with one big star. It starts with two dead ones, two neutron stars. Each one is the crushed core of a sun that's already died. A teaspoon of that material would weigh 1 billion tons. Their spheres may be 12 miles across, but they have the mass of our entire sun. And sometimes these things are born in pairs. They're locked in an orbit, and that orbit decays. For millions of years, they spiral inward, closer and closer. They lose energy as gravitational waves ripples in space-time. Their final dance takes just milliseconds. They don't just collide, they shred each other apart. The tidal forces are so strong, they tear into streams of hot matter before they even make contact. A lot of their material gets flung out into space, and in that ejected material, something happens. The conditions are so extreme, with so many neutrons, that they fuse. They create the heaviest elements. This is the main forge for things like gold, platinum, uranium. The gold in a ring, the platinum in a converter, that was probably made in the death spiral of 2 neutron stars billions of years ago. But the merger does more. In the chaotic center of the collision, a new black hole usually forms right away. And like in the hypernova, some of the swirling debris can get focused into narrow, relativistic jets. The gamma ray burst from this is incredibly short, often less than 2 seconds. These are the short gamma ray bursts, a quick, sharp flash from a different kind of violence. So you have 2 fingerprints, the long, brilliant flash from a dying giant star, and the short, sharp spike from the merger of the dead. One makes black holes and scatters elements like carbon and oxygen. The other scatters the galaxy with gold. It's a profound duality. These events can sterilize whole star systems, but they're also essential creators. They forge the elements that make rocky planets possible, that make life possible. That creative power exists inside a beam of pure destruction, which leads to the most unsettling question. What would that beam do if it were pointed at us? A gamma-ray burst is terrifying because of its focus. It's not a bomb, it's a sniper rifle. The energy from a collapsing star or merging neutron stars gets channeled. It goes into 2 narrow beams firing out from the poles of a new black hole. Like a lighthouse, but instead of a gentle light, its beam is particles and radiation. Moving at over 99.99% light speed, that's a relativistic jet, and the physics does something extraordinary. Because the jet material is moving so fast, the energy doesn't spread out. It gets focused forward, concentrated along the beam's axis. That's relativistic beaming. To a planet sitting right in the path, the burst is unimaginably bright. But to a planet just a few degrees off to the side, it might be completely invisible, or just a faint, ordinary supernova, which explains a cosmic irony. These are the most powerful explosions in the universe, yet we see so few. Our galaxy is filled with the remnants of dead massive stars, binary neutron stars. The events themselves probably aren't that rare, but the beams are so narrowly focused they miss almost everything. For every one we see, hundreds or thousands are pointed into empty space. That focus is what makes them dangerous to life. A supernova's energy washes over a huge volume. It diminishes with distance, but a gamma-ray burst's energy is delivered like a spear. It doesn't diminish the same way over short distances within a galaxy. If Earth were looking down the barrel of that cosmic rifle, the entire energy of a hypernova would be delivered straight to our atmosphere. The question isn't about seeing a bright flash. It's about what that concentrated energy would do to a living world. That first flash is a direct hit. The most penetrating radiation the universe makes, gamma rays, they're photons with so much energy they pass through most things like they aren't even there. Ionizing radiation, it strips electrons from atoms, breaks the molecular bonds that hold life together. A planet in the beam gets that lethal dose in seconds. The upper atmosphere takes the brunt, but the effect cascades down. Gamma rays smash into air molecules that creates a secondary shower, high-energy particles. The ozone layer, our shield against ultraviolet light, gets chemically shredded. It doesn't just thin, it gets obliterated on the side facing the burst. But the danger doesn't end when the flash fades. What follows is the afterglow. The relativistic jet from the explosion plows into interstellar gas, creates a shockwave. It's like a cosmic traffic jam at nearly light speed, a violent deceleration. It forces the jet's energy to be re-radiated across the whole electromagnetic spectrum. That creates a fading beacon. Astronomers can track it, first in X-rays, then visible light, finally radio waves. This afterglow can linger days, weeks, months. For scientists, it's a gift, turns a brief flash into a lasting signal, something to point telescopes at. Watching it fade, analyzing its colors, they can pinpoint the burst's location. Measure its distance, study the galaxy it came from. It's forensic evidence of the explosion's power, the environment that spawned it. For a world in that beam, though, the afterglow is a prolonged catastrophe. With the ozone layer gone, the planet's surface gets bathed in intense ultraviolet radiation from its own sun that triggers a chain, a biological collapse. Starting at the base, the oceans, the land, the afterglow is a reminder. The initial flash is just the opening act of a much longer disaster, far more insidious. For a long time, gamma-ray bursts were just flashes with no home. No one knew where they were. Were they close or were they far away? That question was everything. It told you how powerful they really were, and for years scientists were divided. One group thought they had to be nearby. They thought maybe the bursts were in a huge spherical cloud around our Milky Way. A galactic halo, that was the safe idea, because the alternative was difficult. If the bursts were farther out across the universe, then the energy needed to make them visible to us, it would be unbelievable. It would seem to break physics, so the halo idea kept things sensible. The other group thought they were cosmological, that they came from distant galaxies, billions of light years away. And if that was true, the energy wasn't just large, it was catastrophic. It would mean reinventing how we thought stars died. This went on, it was a standoff. And it needed something to settle it. That came in 1991. The Compton Gamma-ray Observatory went into orbit. On it was an instrument built to answer this one question. The Burst and Transient Source Experiment, BATSI, its job was simple: watch the whole sky, don't miss anything, and for 9 years it did. It saw thousands of bursts. Then the team made a map, just a dot for each flash in the sky, and what they saw, it was decisive. The dots weren't along the Milky Way's plane, where all our galaxy's stars are. They weren't in a halo around it either. The dots were scattered, perfectly randomly, across the entire sky, isotropic, and a perfectly uniform map like that. There's only one explanation. The sources weren't in our galaxy, they were far beyond it, extragalactic. That one map ended the debate. The safe bet was wrong. The universe wasn't sensible. It was capable of violence on a scale we hadn't really imagined. A gamma-ray burst wasn't a local event. It was a beacon from across the cosmos, a signal of a star's annihilation, coming from a galaxy so far away it existed when the universe was young. To be seen from that distance, the energy release is almost impossible to grasp. In that moment, gamma-ray bursts changed. They went from a curious anomaly in satellite data to maybe the most powerful phenomenon we know of. Astronomers had to face a new reality. Physics could allow that much power, but only in the most extreme situations possible. The search for those situations would lead right back to collapsing stars and crashing stellar corpses, and to a sobering calculation about our own place in a universe that makes such things. That map of random flashes told us they were far away, but how far? We needed a number, a distance, and in astronomy, measuring distance is one of the hardest things. You can't use a ruler, you can't send a probe, you have to read the light itself. For gamma-ray bursts, the key was in the afterglow. After the brilliant flash fades, that lingering light gives astronomers something to work with. They point their biggest telescopes at that fading point. And they break the light apart, they take its spectrum, they spread it out into a rainbow, and they look for very specific dark lines. These are absorption lines. They're like chemical fingerprints, gases in the host galaxy or in clouds between us and the burst. They absorb very specific colors. Each element has its own pattern. And this is where the universe does something. The universe is expanding, space itself is stretching, and as that light travels for billions of years, the light waves get stretched too. They get pulled to longer, redder wavelengths. That's cosmological redshift. The farther the light has traveled, the more the universe has stretched during its journey. The more its signature lines are shifted toward the red. It's a cosmic tape measure. Astronomers know what pattern those lines should make in a lab on Earth. Then they see how much that entire pattern has shifted. The amount of that shift gives them the distance. A small redshift means it's relatively close. A huge redshift means the light has been traveling for almost the entire age of the cosmos, and the numbers they found were staggering. One of the record holders is GRB 090423. Its afterglow showed a redshift of 8.2. That single number means a view back in time to when the universe was 630 million years old. It's a glimpse into the cosmic dawn. The star that died to create that flash was among the very first generations of stars. Its light has been traveling toward us for over 13 billion years. We are just now seeing the echo. Establishing these distances did more than satisfy curiosity. It was the final piece, because now, knowing exactly how far away it was, astronomers could work backwards. They could calculate how much energy actually left that dying star, and the answer would force us to rewrite what is physically possible. That redshift was 8.2. And that number, it meant the light had traveled from the very edge of the visible universe. For something to be visible from that far, it couldn't just be a supernova. It had to be more, so they did the math. They took the brightness we measured, factored in that impossible distance, and worked backwards to the source. The energy required was abstract. A typical gamma-ray burst releases something like 10 to the 44 joules. To grasp that, you think of Einstein. E equals mc squared, mass converted to energy. Take our sun, all of it, every atom. Its total mass is about 2 times 10 to the 30 kilograms. If you could convert the entire sun to energy in an instant, you'd get roughly 10 to the 47 joules. A gamma-ray burst is in that territory. It's converting a substantial part of a star's mass into pure energy. In seconds. This isn't fusion. It's not even normal stellar collapse. It's matter-antimatter levels of efficiency driven by gravity and a black hole being born. For context, a supernova, like when Betelgeuse goes, it'll outshine the galaxy. That releases about 10 to the 44 joules, a staggering amount, but a gamma-ray burst is that same energy times 10,000. It's not a bigger bang. It's a different category. The difference is a firecracker next to a thermonuclear blast. One is impressive, the other is apocalyptic, and in a burst, that energy isn't expanding in a sphere. It's focused, beamed into 2 narrow jets. That concentration, that's what makes it a threat. All that power, a sun's worth of mass turned to light, focused into 2 lances. It forces a question. If one of those beams found Earth, what would it do to this thin layer of air and water we live on? The initial flash isn't the real threat. It's what happens after. When those gamma rays hit the atmosphere, they don't just go through. They start a chain reaction. The photons hit the nitrogen and oxygen molecules up there. They break them apart. That creates a shower of free radicals and ions, a reactive soup. And in that soup, new things form. Nitrogen oxides, nitric oxide. Nitrogen dioxide. In the stratosphere where the ozone layer is, these become saboteurs. They start a catalytic cycle. a nitric oxide molecule finds ozone. It steals an oxygen atom and breaks the ozone apart. The nitric oxide becomes nitrogen dioxide. Then that nitrogen dioxide can react with a free oxygen atom. It releases the stolen oxygen and turns back into nitric oxide. The nitric oxide isn't used up. It's a catalyst, a machine for breaking ozone. It can do this tens of thousands of times before it finally drifts down. One burst could fill the upper air with enough of these catalysts to take the planetary shield apart for 10 years. So the result isn't a quick blast. It's a long, global collapse. Imagine over a few months the filter in the sky just goes away. The ultraviolet from the planet's own sun, once blocked, now pours down. This isn't a sunburn. It's a biological catastrophe at the cellular level. UVB and UVC radiation are mutagens. They shred DNA. They break life's instructions. The first to go are the base of the food web. In the oceans, phytoplankton. Those microscopic algae near the surface make a lot of the planet's oxygen. They're the base of the marine system. Under an unfiltered sun, their populations crash. On land, plants suffer. Seedlings fail, leaves are damaged, so photosynthesis drops. The whole system starts to starve from the bottom. For larger animals, for any complex life, the effects are deep. Skin cancers become common, immune systems weaken. Reproduction gets disrupted. A world in this prolonged ultraviolet spring would see ecosystems come apart, not with fire or quakes, with a silent, creeping sickness. Food chains collapse, species that can't adapt or find deep refuge vanish. That's the sterilization mechanism, not an instant fire, a slow, global asphyxiation of the biosphere. All from a beam of light from a star that died billions of years ago. It turns a planet's own sun against it, and that raises a possibility, a historical one. Has our own world ever faced that? A gamma ray burst hitting Earth directly. It wouldn't be like any natural disaster we know. You'd see a light in the sky first, brighter than 1,000 suns. But that light is pure radiation. In just the first few seconds, the upper atmosphere doesn't just absorb it. It gets torn apart. Gamma rays strip electrons from air molecules with so much force the sky turns to plasma. A superheated, electrically charged firestorm covering the whole daylight side of the planet. It's not just a light show, it's a change in the chemistry of the air itself. All that ionization sets off a chain of reactions. Nitrogen and oxygen atoms ripped apart, recombine into nitrogen oxides. Huge amounts of them, they rise and spread. They react with water vapor and create a corrosive rain, nitric acid, falling globally. And at the same time, nitrogen dioxide, that reddish-brown gas, it builds up. It could form a toxic smog so thick it starts to blot out the sun. The world dims into a twilight haze for months, maybe years. That's the immediate aftermath. The atmosphere, our protective blanket, turned into a corrosive, darkening shroud. But the assault is more direct than that. For any life on the surface or in shallow seas, the radiation dose in those first seconds would be catastrophic. Complex organic molecules, the foundation of life, proteins, DNA, cellular membranes, they'd be shattered by the ionizing barrage. It would be a planetary reset. Not an extinction, a sterilization. Every ecosystem, from the deepest forests to microbial mats in thermal vents, would face the same unsurvivable stress at once. This feels like science fiction, a cosmic horror story, but it's physically possible. It's written into the laws of astrophysics, and that forces a question. An unsettling one about our own past. In Earth's 4.5 billion-year journey around the galaxy, has it ever looked down the barrel of that gun? The cosmic sterilization event, it's not just a thought experiment. It has a name, the late Ordovician mass extinction. That was about 445 million years ago. It was the second worst extinction we know of, and the cause has been a puzzle. There's no impact crater from that time, no sign of huge volcanic eruptions like the ones that came later. The clues point somewhere else. The extinction came in two sharp pulses, maybe 1,000,000 years apart, and it hit ocean life the hardest, the creatures in the shallow, sunlit water. Trilobites, brachiopods, graptolites, even the plankton, the base of everything, it suffered a severe decline. It was like something stripped away a protective shield, letting a flood of ultraviolet light into the upper oceans for a long time. That pattern fits one stressor, a rapid loss of the ozone layer. So the question became, what could destroy the ozone layer globally? Not once but twice. One answer that fits speculatively is a gamma-ray burst, not from far away but from somewhere nearby in our own galaxy. If it happened within 6,000 light-years or so, its beam could have delivered a direct hit. Not instantly lethal, but direct. The initial flash might have triggered the first ozone collapse, the first pulse of extinction, then the afterglow, the chemistry it started in the atmosphere that could have caused the second collapse 1,000,000 years later. As the planet tried to recover, it's still just a hypothesis, hard to prove an event that leaves no crater, only a signature in the rock and in the loss of life. But the power of the idea is in the questions. It frames these bursts not as distant curiosities, but as possible agents of macroevolution, right here. They could be a cosmic filter, a rare, devastating mechanism that reshapes the tree of life, and that shifts the perspective from a historical what-if to something else. If it's possible in our past, what does that mean for our future in this galaxy? Our place in the galaxy is a key part of this. To know if we're a target, we have to consider our address. We're not just anywhere. We orbit a star on the inner edge of a minor spur, sitting between two of the Milky Way's major spiral arms. That location, it's more than just the view. It's a sheltered spot, and that shelter connects directly to what makes the most dangerous gamma-ray bursts. The long bursts, the ones from collapsing massive stars, they're picky. They don't come from every giant star. They need a specific type, a star that's not just huge but also poor in metals. That means any element heavier than hydrogen or helium. In the early universe, stars were made of just those primordial elements. Those first giants lived fast, died young, and exploded violently, spreading the first metals into space. Over time, galaxies got enriched. That's the important part. A star born from metal-rich gas, it loses mass as it ages. Powerful stellar winds strip it away, like a storm stripping leaves from a tree. By the time it's ready to die, it's shed so much weight that its core collapse might not be violent enough. It might not create the relativistic jets needed for a long burst. But a star from metal-poor gas, it holds onto its mass. When its core finally collapses, it goes down with everything it has. That makes the hypernova, the focused beams, far more likely. So where do we find these metal-poor, fast-living giants now? They're born in the galaxy's nurseries, the great spiral arms. Those are regions of active, chaotic star formation, filled with the giant clouds that create new stars. If our solar system were inside one of those busy arms, our odds of having a nearby progenitor star would be much higher, but we're not. We're in the local spur, the Orion spur. It's a bridge of material between the Perseus and Sagittarius arms. This area is quieter. Star formation here is more settled. The gas around us has been recycled through many star generations, so it's metal-rich. The massive stars that do form here are the wrong kind for long bursts. They're too polluted with heavier elements to become that kind of weapon. This leads to a bigger idea, what some call the galactic habitable zone. It's not just about liquid water. It's about a region far enough from the chaotic, dangerous galactic center to avoid radiation and disruption, but also a place in a quiet suburb, sheltered from the frequent supernova in the dense spiral arms. Our location seems to fit. We're in a galactic sweet spot, distant from the most violent stellar factories. That geographical analysis gives a first layer of reassurance. Our cosmic neighborhood looks like it's been a stable, sheltered harbor for billions of years, but shelter isn't a guarantee. It just changes the odds. To really weigh the risk, we have to ask not just where we are, but what's actually out there that could still take a shot. Eta Carinae is a hypergiant star, one of the most luminous objects we know of, and it's unstable. Back in the 1840s, it had a major eruption. For a while, it was the second brightest star in the sky. Now it's surrounded by this nebula, the homunculus, shaped like an hourglass made of its own expelled material. Astronomers are sure it will go supernova. Maybe in the next 100,000 years, but whether it could make a gamma-ray burst that comes down to composition. Eta Carinae is metal-rich. It formed from gas already enriched by earlier stars. So it has fierce stellar winds, it loses mass. By the time its core collapses, it may have shed too much of its outer layers. You need those layers to form the tight disk, the focused jets, for a long gamma-ray burst. So its death will be brilliant, a spherical supernova, but probably not a beam. Then there's WR104, a Wolf-Rayet star stripped down in its final phase. It's in a binary system. Its winds collide with its companion's winds. That collision makes a pinwheel-shaped nebula visible in infrared. And that shape is the key. It suggests a rotation axis, a preferred direction. If this star collapses into a hypernova, the relativistic jets would fire along that same axis. So the pinwheel could be showing us where the gun is pointed. The critical unknown is where that axis aims. Some early work thought the pinwheel was nearly face onto us, meaning the pole, a potential jet, could be aimed our way. Later analysis has doubted that alignment. The uncertainty is still there. WR104 is a candidate. It has the right ingredients, maybe the right orientation, but it's not a certainty. Looking around our part of the galaxy, you find a few candidates like this. Massive stars in their death throes, but each one has a list of conditions. All of them have to align. The star has to be the rare, low metallicity type. Its rotation has to be just right to form the disk and the jets. One of those jets has to be pointed right at our solar system, across thousands of light years. And the timing has to coincide with us being here. It's a cosmic lottery. Every condition multiplies the odds against it happening. The probability isn't zero. In a universe this big, this old, nothing is impossible, but it's vanishingly small, astronomically improbable. That's the statistical comfort, but it opens another question. If the immediate threat is that remote, what does the existence of these titans tell us about the universe itself and our fragile place in its violent story? The galaxy gives us a kind of shelter, but shelter is relative over deep time. The real question is probability. How often does the universe roll the dice and land on our number? Astronomers have tried to calculate this, to put a number on the risk. One study by researchers like James Annis looked at the rate of these catastrophic events. Their conclusion was reassuring and also quietly unsettling. In a galaxy like ours, a gamma ray burst powerful enough to sterilize a planet likely happens only once every few 100 million years. Maybe once in a billion years. That timescale is hard to grasp. It means over the entire 4.5 billion year history of Earth, such an event may have happened only a handful of times, if at all, but that's just the frequency of the explosion. For it to be a direct threat, the next condition has to be met. The jet has to be pointed right at us. And those beams are incredibly narrow. They span only a few degrees of sky. It's like trying to thread a needle from thousands of light years away. That narrowness reduces the odds of a direct hit by another factor, perhaps 100 or more. So you multiply these probabilities, a rare event multiplied by a tiny angular chance. The result is an astronomically small annual probability. You are far more likely to win the biggest lottery on Earth a dozen times in a row than to see a sterilizing burst hit our planet in your lifetime. The math is overwhelmingly in our favor on human timescales. But here's the twist: geological time is not human time. Over the lifespan of a planet, over hundreds of millions of years, those incredibly long odds start to shorten. They don't become a certainty, but they become a plausible roll of the dice. What is a near zero chance over a century becomes a distinct possibility over an eon. This transforms the gamma-ray burst from a personal threat into a planetary one. It's a risk that doesn't hang over individuals or even civilizations, but over the entire continuity of complex life on a world. It introduces a profound idea that existence itself at the scale of a biosphere is subject to a persistent, low-probability risk, a background hum of potential catastrophe written into the laws of stellar physics. That has been present since the first stars lit up. This realization isn't meant to cause alarm, but to inspire a deeper perspective. It asks us to consider our place not just in space, but in the immense, patient flow of cosmic time. The Fermi paradox: if the universe is so big and so old with all these planets that could have life, then why is everything so quiet? Where is everyone? One answer might be in what we've been talking about: gamma-ray bursts. They might not just be a danger to one world, they could be a kind of reset button. For whole parts of a galaxy, this is the idea of a great filter, a barrier, something so difficult that it stops life from ever getting to the point where you can see it from across the stars. A bottleneck, and what's a better filter than something that sterilizes a galaxy every few 100 million years? Think about a planet. Life starts, it gets more complex. Intelligence begins, but right when a civilization is about to look outward, to build something that could signal it's there, a flash from a star dying thousands of light years away. It washes over the planet, the ozone is gone, the food web falls apart, the biosphere is reset, all that potential gone. The clock for complex life on that world starts over. From almost nothing. If this happens across the galaxy, not all at once but as a random, repeating event, it explains the silence. Civilizations might appear, but they get cut back regularly. They're like young trees in a forest that has regular, huge fires. A few might survive in protected spots, but they never get old enough to fill the whole forest. The galaxy could be full of the remains of biospheres, worlds that had a chance and then were sterilized, their stories ended by a beam of light they never saw. This makes gamma-ray bursts more than just a physical threat. They become a possible key to a bigger question. They're not just something that could end us. They might be the reason we seem to be alone. It means the universe might not just be empty. It might be a graveyard of potential, kept quiet by the occasional, devastating whisper of a dying star. This quiet graveyard of potential is why we keep watch. To understand the filter, you have to see it clearly, map its frequency, its power. For the last 20 years, that watch has been kept by two robotic sentinels in orbit. The first is a satellite named for its speed, NASA Swift mission. Its design is a marvel of reflexes. When its burst alert telescope senses a gamma-ray flash anywhere in the sky, the whole spacecraft doesn't just note it. It pivots. Within seconds, it slews around to point its more sensitive X-ray and optical telescopes right at the source. That reaction time, automated in space. It catches the afterglow early when it's brightest, pins down the location with precision. Lets ground-based telescopes everywhere join the hunt. Before Swift, bursts were fleeting mysteries. After Swift, they became events we could study. From the first second to the fading radio whisper weeks later. Its partner in this watch is the Fermi Gamma-ray Space Telescope. Where Swift is the rapid responder, Fermi is the constant surveyor. Wide-eyed, its primary instrument sees about a fifth of the sky at any moment. It monitors the entire gamma-ray sky every 3 hours. Less about lightning-fast turns, more about building a complete map, a sensitive map of the high-energy universe. Fermi sees the faint bursts, the distant ones. The short spikes from neutron star mergers that might otherwise be missed. Together, these two missions form an early warning network. They're not watching for an imminent threat to Earth. They're cataloging the universe's violence. Every burst they detect adds a data point. It tells us how often these events happen, in what types of galaxies. With what energy, this constant flow of real-time data is transforming gamma-ray bursts from mythological monsters into measurable phenomena. We are building a census. A census of cosmic catastrophe. This vigilance, it can't stop a stellar collapse, but it does something profound. It quantifies the danger. It turns the unsettling idea of a great filter into a set of numbers. Numbers we can actually work with. We're not just speculating about ancient extinction events anymore. We are watching the mechanism itself at work in galaxies far across time and space. That knowledge gathered by our silent robotic watchers is the first step, the most crucial step in confronting any cosmic risk. A flash of light is just one part of it. Astronomy for so long was just sight, reading the universe by its light, but the most violent events, they speak in other ways, ways we've only just started to hear. When a huge star collapses or two neutron stars come together, that cataclysm doesn't just send out gamma rays, it might whisper in two other forms. Much harder to detect, the first whisper is like a ghost, a neutrino. These are fundamental particles, but they're strange, almost no mass, no electric charge. Which means they hardly ever touch normal matter. Trillions are going through you right now, from the sun, from deep space, and you feel nothing. They pass right through the planet. In a gamma-ray burst, the conditions in that collapse or merger should create a huge flood of them, a neutrino burst. And since neutrinos ignore gas, dust, magnetic fields, they'd get here first. Minutes or hours before the light, they're the first silent warning. To catch these ghosts, we built traps in strange places. The Ice Cube Neutrino Observatory. It's not a telescope on a mountain. It's a detector buried in the Antarctic ice. Over 5,000 sensors frozen into a cubic kilometer of ice, more than a mile down. They wait for the extremely rare moment a neutrino from deep space actually hits an atom in the ice. That collision makes a faint blue flash. Ice Cube's job is to see that flash, trace its path, point back to where it came from. It's listening for the quietest signals. The second whisper is deeper. It's a ripple in space and time itself, a gravitational wave. Einstein predicted them a century ago. They're not light or matter, they're distortions. When massive objects accelerate violently, like two black holes or neutron stars spiraling together, they shake spacetime. They send out waves like ripples. These waves stretch and squeeze everything they pass, but by an amount that's almost impossible to measure. For decades, it was just theory. Then, in 2015, LIGO heard its first chirp. The sound of two black holes merging over 1 billion light-years away. It was a new sense turned on. For short gamma-ray bursts, the ones from neutron star mergers, this was the key. In 2017, LIGO and Virgo detected ripples from two neutron stars colliding. 2 seconds later, telescopes in space saw a short gamma-ray burst from the same spot in the sky. For the first time, we witnessed one cosmic event with two different senses. We felt the space-time shake, and then we saw the flash. That multi-messenger event changed everything. It proved without question that neutron star mergers cause short bursts. It let astronomers find the exact galaxy. They pointed every telescope at that spot, watched the afterglow for weeks. In that glow, they saw the signs of heavy elements being made, gold, platinum, blown into space. We were watching the universe's forge in real time. So this is the new era. We're not just astronomers anymore. We're learning to speak multiple languages. We listen for space-time ripples with LIGO and Virgo. We wait for the ghostly neutrino signal from Ice Cube, and we watch for the flash with Swift, Fermi, all the telescopes. When these signals line up, we get a complete, inside-out view of the most extreme physics. We don't just see the fireball, we sense the engine behind it. We hear the black hole being born. That full picture turns a gamma ray burst from a sudden flash into a detailed story. A story told in gravity, in ghosts, and finally, in light. Even with all these different ways of looking at them, the catalogue of bursts still has puzzles. Some flashes don't fit into the two main categories. They're too faint or too long, or they repeat. They point to engines we haven't fully imagined. And that's where theory goes, into these extreme possibilities. One candidate is at the intersection of a neutron star's death and its second life, a magnetar. It's a neutron star, but not an ordinary one. It's born spinning incredibly fast, and it has a magnetic field of almost incomprehensible strength. A typical neutron star's field is already 1 trillion times stronger than Earth's. A magnetar's field is another 1,000 times stronger than that. If one were halfway to the moon, its magnetic field would erase every credit card on the planet. It's a cosmic magnet of pure destruction. This titanic magnetic field is under immense stress. It warps the star's solid crust, which is a lattice of atomic nuclei. And occasionally that crust can crack, a starquake, or the magnetic field lines can snap and reconnect violently, releasing a torrent of energy. Theorists think an event like that on a young, hypermagnetized neutron star could power a different kind of gamma-ray flash. One that's less energetic than a full hypernova beam, but potentially repeating. It could explain some of the odd, softer gamma-ray repeats we've seen. So here, the engine isn't a collapsing star or a merger. It's the apocalyptic magnetism of a newborn stellar corpse shaking itself apart. The search for explanations goes further into the speculative. Could some brief flashes come from the evaporation of tiny, primordial black holes? These are hypothesized relics from the universe's first second, or from annihilating clumps of dark matter. These are frontier ideas, not mainstream, but they show a crucial point. The story of gamma-ray bursts isn't a closed book. Every anomalous flash, every piece of data that doesn't quite fit, forces astrophysicists to probe the absolute limits of known physics. It reminds us the cosmos has a deeper bag of tricks than we've catalogued. Our understanding is a map, and the territory of stellar death is still being explored, one violent, luminous clue at a time. But inside that violence, the universe is also building. It's creating. The same kind of cataclysm that could end a world is actually responsible for making some of the things that let worlds exist at all. That's the surprising part about these titans. They're not just destroyers, they're also cosmic benefactors, and the evidence for that came from that historic detection in 2017, when gravitational waves and a short gamma-ray burst came from the same neutron-star collision. Telescopes watched the afterglow for weeks, and in that fading light they saw something extraordinary, the signature of heavy elements being forged in real time. It's called the Rapid Neutron Capture Process, or the R process for short. That's how you build atoms heavier than iron. In the extreme conditions of a neutron-star merger, matter is incredibly dense, flooded with free neutrons. Atomic nuclei can capture neutrons faster than they can decay. They climb the periodic table rapidly. This process, it takes just seconds. It creates elements like gold, platinum, neodymium, uranium. The material ejected in that violent merger, glowing in the afterglow, was seeding space with these heavy, precious atoms. The gold in your jewelry, the platinum in a catalytic converter, the uranium in some reactors, they were likely born in a cataclysm like that, billions of years ago. The merger didn't just make a flash, it made future possibilities. That enriched debris, flung out at incredible speeds, eventually mixes with the vast clouds of gas and dust between the stars. Over millions of years, that cloud, now carrying these new heavy elements, can collapse again, to form a new generation of stars, and around those stars, rocky planets can coalesce. Planets with iron cores, silicate mantles, the complex chemistry that might one day lead to life. So a gamma-ray burst in its death throes is scattering the essential ingredients for new worlds. It's a creator as much as an eraser, and that transforms the entire narrative. The same beam that could sterilize a planet is a direct result of an event that, billions of years earlier, may have provided the very materials that made that planet rocky and metallic to begin with. It's a beautiful and terrifying cycle. The universe uses its most violent mechanisms to build the foundations for complexity. It means we're not just bystanders in a dangerous cosmos. We are, in a very literal sense, the children of its violence. The iron in our blood, the gold in our circuits, the uranium in the earth, they are stardust, yes. But some of them are the ashes of the most apocalyptic explosions imaginable. Our existence is intertwined with the very phenomena that could, under different circumstances, erase us. That's the profound duality, a cycle of creation and destruction on the grandest scale, where endings are always, somehow, also beginnings. This cycle of creation and destruction, it doesn't just happen on one world. It works across the whole galaxy. It's its own kind of ecology. A gamma-ray burst, it can sterilize every planet in its path. That's a local catastrophe. But the shockwave from that same event, that shell of energy and enriched material, it keeps going. It travels for light years, and it can run into these vast molecular clouds drifting between the stars. The nurseries for new solar systems, that shock compresses the gas. It triggers new rounds of star formation, so a single death plants the seeds for thousands of new births. The galaxy gets reshaped by these explosions. Its spiral arms, its star-forming regions, they're influenced by the echoes of ancient hypernova, which leads to a speculative possibility. Could a violent event also spread life? The idea is called Panspermia. It suggests life, or the complex molecules that lead to it, might not start fresh on every world. It could be transported between planets, even between stars on natural spacecraft. Rocks blasted off a planet by a major impact. For a gamma-ray burst, the energy, even at a distance, could send powerful shockwaves through a planetary system. It could dislodge countless fragments from a world's crust, send a cloud of debris into space, and some of those rocks, if they had hardy, dormant microbes deep inside, they could become interstellar travelers. Shielded by the rock from radiation and vacuum, they could travel for millions of years, frozen. Eventually, the gravity of another star might capture one of these wanderers. It could fall as a meteorite onto a young, wet world. If conditions were right, those microbial hitchhikers might wake up, find a new home, so a gamma-ray burst becomes a kind of gardener. A paradoxical one. It might wipe the slate clean in one corner of the galaxy, but its shockwave could kick-start a diaspora of life from another. It frames the galaxy not as a static collection of stars, but as a dynamic, interconnected ecosystem, where catastrophe and dissemination are two sides of the same coin. The same force that imposes a filter on life in one region might be the delivery service that plants its seeds in another. This doesn't answer if it's happened, but it expands the story. It suggests the ingredients for life, maybe life itself, could surf the shockwaves of the universe's most violent storms, turning a story of pure endings into one of unexpected, distant beginnings. The real danger now might not be extinction. It could be a blackout. Our world, with all its electronics, is more fragile than our biology in this case. A gamma ray burst from a nearby star a few thousand light-years away wouldn't have to sterilize the planet to stop civilization. It just has to pass through the atmosphere. The intensity of those gamma rays would ionize the upper air violently. It would create a dense, temporary layer of charged particles. That layer would act like a radio mirror, but a chaotic one. It would scatter and absorb the high-frequency radio waves we use for long-distance talk. For minutes, maybe hours, global radio could go down. More than that, the signals from GPS satellites, which travel through that same layer to reach us, would be scrambled. The precise timing those signals depend on would be thrown off, so it's not just a lost map on a phone, it's the loss of precision timing for financial networks. The disruption of navigation for planes and ships, the temporary blinding of countless systems that quietly rely on GPS to function, but the assault could go deeper. Those gamma rays and the secondary particles they create would also induce powerful electrical currents in the ground, in long conductors. This is the idea of a geomagnetically induced current. Our whole power grid, that vast web of transformers and lines, acts like a giant antenna for this kind of event. A sudden, intense pulse from a nearby burst could push massive, destabilizing currents into that grid. Transformers, the huge and hard-to-replace hearts of the system, could be overloaded. They could overheat and fail. The cascade could lead to widespread, long power outages. Not from a storm, but from a star. Recovery would take months, not days, sourcing and replacing those critical components. Above us, the satellites in orbit would face their own crisis. Beyond the communication problems, the intense radiation from the burst would flood through their electronics. It could cause single-event upsets, random bit flips in memory. Or worse, permanent damage to sensitive solar panels and internal parts. Our orbital infrastructure, from weather watching to telecom, could be degraded in an instant. This shows a different kind of vulnerability. It means even if a burst is too far away to harm life directly, its reach could still find the technological weak point of an advanced civilization. We've built a web of incredible complexity, but in doing that, we may have traded one risk for another. The cosmic environment that let life evolve now holds a phenomenon that uniquely threatens the systems life has built. It shifts the view from ancient mass extinctions to a very modern, sobering possibility. It makes us consider not just the survival of life, but the resilience of everything that life at our stage depends on. GRB 980425, that was in April of 1998. The satellite that found it was Bepo-SAX. This was before Swift, before Fermi. Finding the Afterglow was still new. This one was close, about 140 million light-years, in a galaxy called ESO 184G82. That's very close, and it was faint. For a gamma-ray burst, it was dim. That faintness was the clue. It meant we weren't looking down the beam, we were seeing it from the side. The main energy was pointed somewhere else. We saw the spillover, the fringes. Then, in that same galaxy, they found a supernova, SN 1998 BW. And it wasn't a normal one, it was incredibly bright. Its spectrum showed it was expanding at a huge fraction of light speed, a hypernova. The two events, the burst and the supernova, were in the same place. And they happened at the same time. That was the proof, direct proof that some long gamma-ray bursts are the death of massive stars, seen with a supernova's fireball. GRB 980425 was the burst from the cheap seats. SN 1998 BW was the star that made it. That proximity is the sobering part. 140 million light-years is vast, but it's a neighbor. It means the engine for these events exists in galaxies like ours. The universe is still making them. Right now, nearby, we just saw this one from a safe angle. If that galaxy had been rotated, if the poles were aimed at us, it would be different. The flash wouldn't have been faint. It would have been devastatingly bright. That observation did two things. It confirmed a major theory, gave scientists a crucial piece, and it was a quiet, chilling reminder. The Titans are real. They're not just from the early universe or distant galaxies. They happen here and now. A star in a galaxy you could see with a backyard telescope can do that. Our safety might not be about the beast being absent. It might just be the random geometry of where we stand. In October of 2022, there was a gamma-ray burst. They called it the boat, the brightest of all time. Its official name was GRB 221009A. It came from a part of the sky hidden behind dust from our own galaxy. But it was so bright it saturated every gamma-ray detector that saw it. Instruments on the Swift and Fermi spacecraft were blinded by it. This flash came from almost 2 billion light-years away. And it was so powerful it ionized the upper part of Earth's atmosphere. It actually disturbed our ionosphere from that distance, which tells you about the energy involved. 2 billion light-years is far, but it's not the early universe. The star died when the cosmos was already mature, so that potential for catastrophic violence isn't just from the primordial past. The universe can still make these explosions now. The boat brightness was a direct challenge. It pushed our instruments to their limits. It made scientists ask what could make something that luminous. The answers started to come from the afterglow. Telescopes on the ground and in space watched the light fade across different wavelengths, and they saw something unusual. The area around the exploded star was very clean. There wasn't much material nearby. That's a critical clue. For a gamma-ray burst's jet to punch out and shine that bright, it needs a clear path. If the star had shed lots of gas and dust at the end, creating a dense cocoon, the jet would have to fight through it. It would lose energy. The burst we'd see would be dimmer, muddied. The boat's clean surroundings mean its star was relatively quiet at the end. Maybe it shed its outer layers in a gentle, steady wind, or maybe it held onto them until the final collapse. Either way, it left a clean corridor, so when the core collapsed and the black hole formed, those focused beams could erupt into space almost unimpeded. All that catastrophic power was channeled straight into the beam we saw. Nothing scattered it or absorbed it along the way. It was a perfect escape, a perfectly violent one. Studying this is like looking at forensic evidence from a stellar crime scene. The cleanliness tells you about the star's personality in its last millennia. It wasn't a violently erupting monster like Eta Carinae. It was a giant that met its end with a strange, quiet preparation that set the stage for the most brilliant flash we've ever recorded. So the boat is more than a record holder. It's a masterclass, a recent, nearby example of the ideal conditions for making the ultimate cosmic beam. It confirms our models. And it humbles us. It reminds us the cosmos can still produce energies that strain the very tools we use to understand it. That perfect violence from the boat, we can't recreate that in a lab. But we can build it inside a computer. To really understand what happens in those seconds, scientists use the most powerful supercomputers. They run simulations of a star collapsing. These aren't just animations, they're solving the fundamental equations of physics for millions of virtual particles, all of them interacting under extreme gravity, extreme temperature, extreme pressure. This is computational astrophysics. It's become our only window into the engine of a gamma-ray burst. You start with a model of a dying, massive star. The simulation tracks the collapse of its iron core in real time, down to fractions of a second. The core crushes into a black hole, and the infalling material forms a disk. A swirling, superheated disk. This is where the magic happens, and the immense computational challenge. The models have to account for the physics of this environment. They use hydrodynamics to simulate the flow of matter like a cosmic fluid, but that's not enough. The magnetic fields are crucial, so they add magnetohydrodynamics. modeling how these unbelievably strong magnetic fields get twisted and amplified by the spinning disk. It's this magnetic tornado, channeling energy along the star's rotation axis, that theorists think helps launch the jets. Helps collimate them. Getting these simulations right is a monumental task. They push supercomputers to their limits, running for months on thousands of processors just to model a few seconds of cosmic time. Why go to that trouble? Because these virtual labs answer questions telescopes can't. They show if a jet, once launched, stays stable as it punches through the star's outer layers. Or if it wobbles and dissipates. They calculate the efficiency, how much of the gravitational energy from the collapsing star gets converted into the beam's raw power. And how much is lost. That efficiency number is vital. It tells us, in the end, how bright a burst can be. The simulations also trace the jet's journey after it escapes the star. They model how it plows into the surrounding interstellar medium, creating the forward and reverse shocks that power the long-lasting afterglow we see. By tweaking the initial conditions, the star's mass, its rotation speed, its magnetic field, scientists can run countless virtual experiments. They can see which combinations produce a brilliant, focused beam like the boat, and which ones produce a fizzle. This virtual modeling has a very practical application, a sobering one. It lets researchers move past general warnings. They can calculate with more precision what a nearby burst would do to a planetary environment. By understanding the exact spectrum of radiation the jet produces, and how that radiation interacts with different atmospheres, they can model the cascade of chemical destruction. They can simulate the formation of nitrogen oxides, the erosion of the ozone layer, the resulting ultraviolet flux at a planet's surface over years. This turns cosmic sterilization from a frightening idea into a quantifiable set of environmental parameters. It tells us not just that a burst is dangerous, but exactly how its danger would unfold over time. For any world in its path, these digital star deaths born in silicon and code, they're more than academic exercises. They're the tools that let us measure our own fragility. Against the universe's most powerful engines, that search for past events, it isn't just in computer models, it's happening right here in the ground. To know if a gamma-ray burst has ever hit us, scientists become detectives. They sift through the Earth's own archives, looking for a specific kind of evidence. A chemical fingerprint. The idea is that a nearby burst would have showered our atmosphere with radiation, altering its chemistry, leaving a permanent mark. These marks would be subtle, written not in ash or bone, but in the precise ratios of atoms, in ancient rock, in ice, in the rings of long-lived trees. One key element they hunt for is an isotope called iron-60. It's a radioactive form of iron that isn't made on Earth. It's forged in massive stars and scattered by supernova. So if a layer of sediment shows a spike in iron-60, it's a sign that debris from a nearby stellar explosion rained down on us. Researchers have found such layers. They correspond to supernova that happened a few million years ago, relatively close by. But a supernova is not a gamma-ray burst. Finding iron-60 tells us a star died nearby. It doesn't tell us if its death was a spherical explosion or a focused beam, so it's a clue to a violent neighbor, but it's not the smoking gun for a direct hit. The more direct signature would be in the atmosphere itself. A burst's radiation would have dramatically increased the production of certain radioactive isotopes, like carbon-14. This isotope is naturally made when cosmic rays hit nitrogen in the air, but a massive surge from a nearby burst could create a global spike. Scientists look for this in tree rings and ice cores, which preserve annual layers. A single, massive, worldwide spike in carbon-14 across all records from a specific year would be a startling signal. So far, no such unambiguous spike has been found. We see smaller variations linked to solar activity, but not the catastrophic global event a burst would cause. Another potential fingerprint lies in nitrogen. The intense radiation could convert stable nitrogen-14 into its heavier cousin, nitrogen-15, at an unusual rate. This could leave an isotopic anomaly in nitrate deposits trapped in polar ice. Teams have drilled deep into the Antarctic and Greenland ice sheets. They analyzed tiny bubbles of ancient air, searching for these odd ratios. It's painstaking work. Like looking for a single altered grain of sand on a vast beach. The search continues, but no definitive signal has emerged. This absence of evidence is meaningful. It suggests that if a sterilizing burst has ever hit Earth, it was in the very deep past, perhaps before complex life arose, and its record has been erased by the constant recycling of the planet's crust. Or, more reassuringly, it suggests our solar system has been fortunate. We may have always been in the quiet suburbs, or the beams have always missed. This turns our entire planet into an ongoing detective story. Every ice core pulled from the poles, every ancient seabed sediment core, is a page in a cosmic logbook. We are reading our own history, not just of climates and volcanoes, but of the stars that lived and died around us. The search for these isotopic ghosts is a silent testament to an idea. Our world is not an isolated island. It is a document recording the violent history of our galactic neighborhood. The fact that we can look for these clues, that we have the curiosity to ask these questions, is itself a kind of answer. It means we are awake in a universe that holds such secrets. The search for those isotopic ghosts, it's more than just science. It's a philosophical search. And it makes us face a basic truth about where we are. Gamma-ray bursts, with all their terrifying power, they're the final statement of cosmic impermanence. They remind us that a world full of life, a biosphere built over billions of years, it exists under a sky that can turn hostile without warning. Our existence isn't guaranteed by the universe. It's a temporary arrangement, matter and energy in a quiet corner during a relatively peaceful time. That perspective is humbling. It scales our human concerns against the patient, indifferent forces that shape galaxies. But the fact we're here to even think about this threat, that suggests a counterpoint, resilience. If the late Ordovician idea holds any water, then our planet has already taken a significant cosmic hit. Life was pushed right to the brink, but it didn't end. It adapted, it found new forms, it diversified. After that pattern repeats, all through Earth's deep history. Catastrophe clears the stage. It makes room for new evolutionary acts. The biosphere's resilience isn't a gentle persistence. It's a stubborn, creative force. Operating on geological timescales, it means life, once it gets a foothold, is incredibly tenacious. It can endure events that reshape the surface of its world. So you have this duality, the profound fragility of our specific moment, set against the deep time resilience of life itself, and that frames a crucial question for our civilization. We're the first species here to become aware of these cosmic dangers, the first to read the warning written in the light of dying stars. With that awareness comes a unique responsibility. Our technological civilization, for all its power, has added new layers of fragility. A nearby burst might not sterilize Earth, but it could collapse the global systems we depend on. Our resilience isn't just biological anymore. It's technological, social, logistical. That shifts the imperative for space exploration from a purely exploratory or economic endeavor to a matter of long-term survival. Becoming a multi-planet species isn't about planting flags or harvesting resources. It's about ensuring the thread of consciousness, the story of life that's unfolded here, isn't tied to a single point of failure. By establishing independent communities on other worlds, Mars, maybe, or in free-floating habitats, we create a backup for humanity. We spread the risk. A catastrophe on one world wouldn't mean the end of our collective journey. It's the ultimate application of the resilience we see in nature, but directed by intelligence and foresight. We'd be learning from the cosmos itself, using its own harsh lessons to secure a future that can outlast any single stellar event. So in that light, looking to the stars becomes the most profound act of care. For the legacy of life on this pale blue dot, the galactic habitable zone isn't a fixed map, it's a story that changes. It makes you think about habitability in deep time, not just space. For complex life, a planet needs more than the right distance from its star. It needs a quiet neighborhood, and it needs that quiet to last for billions of years. So the frequency of gamma-ray bursts becomes part of the timeline. The early universe was more violent, galaxies were smaller, star formation was frantic. The gas clouds were pristine, lacking heavy elements. That was the perfect recipe for long gamma-ray bursts, massive, metal-poor stars. They were everywhere. The first few billion years likely had a much higher rate of these explosions. Any young planet then, in any spiral arm, even in the outskirts, faced a higher chance of being sterilized. The universe was flashing with these beams, making it very hard for life to get a stable foothold. In that epoch, the galactic habitable zone might have been incredibly narrow. Or maybe it didn't exist at all. Life would have been constantly reset, but the universe aged. Stars lived and died. They enriched the galactic gas with heavier elements. Over eons, the average metallicity increased. That meant fewer of those metal-poor giants. The rate of the dangerous long bursts began to decline. The galaxy grew up. It became less chaotic. Regions that were once deadly became safer. This is a temporal filter. A planet that forms too early, even in a perfect location, might be wiped out before life gets past single cells. A planet that forms later, like Earth, enters a galaxy that has quieted down. We appeared at a time when the spiral arms, while still active, weren't producing bursts at the same furious pace. Our solar system's location in a quiet spur, combined with its birth date 4.5 billion years ago, placed us in a spatial and a temporal sweet spot. We are here not just because of where we are, but because of when we are. The window for a long biological narrative had finally opened. This layered requirement, the right place and the right time, makes observers like us seem even more remarkable. It suggests cosmic history itself had to mature. It had to settle before the stage could be set for a story as long and complex as our own. That long window of cosmic safety is a gift. But it's not a guarantee, so you see the threat coming. Could you stop it? That's where you move from understanding the danger into far future speculation. Science meeting engineering dreams. Imagine a society that's mastered its star system. They see a hypergiant star in a neighboring system. It's beginning its final, unstable wobble. They calculate its collapse is imminent, and worse, its poles are aimed right at their home world. What could they do? The first line of defense might be magnetic. A gamma-ray burst jet is a torrent of charged particles. Electrons, protons, atomic nuclei, all moving at nearly light speed. A powerful enough magnetic field, generated on a planetary scale, could deflect those particles. Picture a network of orbital stations, or a single colossal structure at a stable point between the planet and its star, generating a magnetic bubble vast enough to envelop the entire world. The energy required would be staggering, maybe harvested from their star itself. That wouldn't stop the initial gamma rays, those are uncharged photons. But it could sweep aside the lethal particle storm that follows, mitigating the worst atmospheric chemistry. The second, more subtle challenge is the ozone. Even if the particles are deflected, the gamma rays themselves would still shred the protective layer. So the defense plan needs a second phase, atmospheric repair. A far future civilization might have fleets of atmospheric processors. Self-replicating nanoscale machines may be already in place as part of their climate stewardship. Upon detection of the burst, these machines trigger into a global emergency protocol. They flood the stratosphere with ozone precursors or catalyze the rapid recombination of oxygen molecules. Trying to rebuild the shield faster than the sun's ultraviolet radiation can pour through, it's a race against time, a planetary-scale medical procedure performed in the sky. These concepts are, for us, advanced science fiction. The energy scales, the material science, the coordination required far beyond anything we can envision building. But they're not, in principle, forbidden by physics. They frame the gamma-ray burst not as an act of God, but as a natural disaster. And humanity has a long history of learning to manage natural disasters. We build levees against floods, early warning systems for tsunamis, reinforced structures for earthquakes. The difference here is one of scale, moving from planetary geology to stellar astrophysics. That shift in perspective is profound. It transforms the narrative from passive potential victimhood to active, long-term responsibility. It suggests the ultimate answer to cosmic threats may not be luck or location alone, but knowledge preparation, the sustained application of intelligence over generations. For a species that survives long enough to see the danger, the greatest challenge may not be the burst itself, but the collective will to build the shields long before they are ever needed. It turns a story about endings into a question, the kind of future we are capable of building. The most violent explosions in the universe might come from places we haven't thought of. Our models for collapsing stars and neutron star mergers work well, but they don't explain everything we see. Some bursts are just strange. They're too faint or too long, or they repeat in ways that don't fit. That's where the frontier opens up, where you have to ask if there are engines we haven't imagined. Something inside the star itself, something invisible, could be the trigger. One idea points to dark matter. We know it's there from how galaxies spin, but we don't know what it is. If certain dark matter particles collect in the core of a massive star, they could eventually annihilate each other. That sudden energy release could disrupt the star from the inside. It might not cause a full hypernova, but it could trigger an unusual outburst that looks like a gamma-ray burst. It's a thought that the invisible scaffolding of the cosmos could become unstable and light a stellar fuse. This connects to other mysteries, fast radio bursts for instance. Those are millisecond radio blips from distant galaxies. Their origin is debated. Some might come from magnetars having starquakes. But could there be a link? Could some short gamma-ray bursts and some fast radio bursts be different signatures of the same event? A neutron star merger might produce the gamma flash, and the turbulent magnetic field around the new black hole could generate a radio pulse. We're just starting to see the universe in this multi-messenger way. Each new detection hints at a richer, more connected tapestry of high-energy phenomena. Considering this isn't about abandoning solid theories. It's about humility. It keeps the field open to discovery. Every anomaly in the data, every burst that doesn't fit, is a potential clue. It reminds us our current models, however successful they are at explaining certain bursts, are still incomplete. They're maps of a territory that's vaster and more mysterious than we can chart. The true nature of gamma-ray bursts may hold deeper secrets, not just about how stars die, but about the fundamental laws governing matter and energy under the most extreme conditions. They challenge us to look beyond what we know and to wonder what else the cosmos can do. These events go beyond just research. They touch something deeper. A kind of wonder. That raw power makes gamma-ray bursts a compelling tool for outreach. They're a perfect gateway. Planetariums use them as centerpieces. You sit in the dark and the dome becomes a window. You see a hypergiant star's final moments, the collapse, the jet erupting, the beam lancing across a virtual galaxy. It's visceral. It turns abstract equations into a story you can feel. Documentaries build narratives around them. They frame them as cosmic detectives. They follow teams of scientists in real time. Alerts come in from Swift and Fermi. They race to point telescopes at a fading afterglow that brings the process to life. It shows the collaboration, the excitement, the frustration. It makes the researchers human. Their quest becomes relatable. This outreach extends into participation. Citizen science. Projects like Einstein at Home let anyone donate idle computer power to analyze data from gravitational wave detectors, from radio telescopes. Your home computer becomes part of the global search, the search for ripples from neutron star mergers. Other platforms let volunteers examine real telescope images. To help classify galaxies that host bursts, this direct involvement demystifies science. It turns the public from observers into collaborators. When a major event happens, like the boat, social media lights up. Discussions, visualizations, explanations from professionals and skilled amateurs. A global conversation ignites, centered on understanding a flash from 2 billion light-years away. For a young student seeing this, the impact can be profound. The scale bridges disciplines. To understand a gamma-ray burst, you need physics for the collapse, chemistry for the atmospheric effects, biology for the impact on life, even philosophy to ponder the implications. It shows that science isn't separate subjects. It's a single, interconnected way of understanding reality. That interdisciplinary thrill can spark a lifelong passion. It inspires the next generation of astronomers and engineers who might design the telescopes, programmers who write the simulations, science communicators who share the stories. By sharing this in engaging ways, we do more than inform. We empower, we give people context to see their own world differently. To understand our peaceful sky is a temporary condition in a dynamic and sometimes dangerous cosmos. That awareness cultivates a deeper appreciation, not fear. It fosters critical thinking, the ability to weigh evidence, understand probability, separate sensationalism from science. In a world flooded with information, these are essential skills. The story of gamma-ray bursts in all its terrifying grandeur reminds us of a privilege. The privilege of consciousness, that we are here in this quiet moment, able to look up, able to decipher the violent poetry of the stars. That privilege of consciousness, it means we have to think ahead. Even about things that seem remote. Imagine a headline, not from fiction but from a major observatory. It says they've identified a clear and present danger. A massive star nearby, maybe a few thousand light-years away. It's entered its final stage. The spectroscopic analysis shows its metal pore, which is the right type. And the imaging shows a structure, a pinwheel nebula, something that indicates its rotational axis. And according to the models, that axis points right at our solar system. The probability of a future gamma-ray burst is high, and we are in the crosshairs. It's a hypothetical, a thought experiment, but following it through shows you something about our world. The immediate reaction would be a global crisis, a kind we've never faced. There's no enemy nation to sanction, no terrorist cell. The threat is a natural object, just obeying physics. Panic would be a real risk. Markets would crash, investors grappling with a future that could be shortened or altered. Long-term planning for anyone, for businesses, for governments, it would become almost impossible. Do you build a new power plant with a 50-year lifespan if the horizon of stability is shorter? The foundations of economic confidence, they're built on the assumption of a continuous future. That would be shaken, but then, paradoxically, it could also trigger the most intense period of investment in human history, scientific, technological. A global threat demands a global response. It would force a level of cooperation we haven't managed on things like climate change. Rival nations would have no choice. They'd have to pool resources, share data, collaborate on a survival plan. The world's scientific talent marshaled toward a single goal, understanding the star's precise timeline. and exploring every mitigation strategy, magnetic shield concepts, atmospheric repair, the budget for spaceflight for planetary defense, it would swell. From billions to trillions, funded by a global consortium, we'd see a new space age, not driven by exploration or profit, but by sheer necessity. This thought experiment forces a question about our priorities now. We allocate vast resources to immediate threats, high-probability ones, pandemic response, military defense, economic stimulus. Those are tangible, present dangers. But we struggle to invest against low-probability risks, ultra-high-consequence ones. The calculus is difficult. How much of our collective wealth, our effort, should go toward a threat that might not materialize for 10,000 years? Or ever, yet if it does materialize, the cost of inaction is total. That's the challenge of existential risk management. It asks us to care for generations we'll never meet. To spend today for a safety we hope is never needed. It's an exercise in foresight, altruism on a species-wide scale. Identifying such a star would collapse that distant future into an urgent present. Make the abstract terrifyingly concrete. Until that day, if it ever comes, the exercise is just a mirror. It shows us what we value, how we cooperate under pressure, and where we choose to look or not look as we navigate a cosmos that's beautiful, bountiful, and quietly dangerous. These cosmic flashes, they come in so many forms. There are the long bursts from giant stars collapsing, and the short ones from neutron stars colliding. But then you have others that don't fit those categories at all. Some last for hours, they're called ultra-long. Others, from the same part of the sky, they repeat. They flicker on and off, which a single collapsing star could never do. Some brilliant flashes, you see a supernova afterward, clear as day in the host galaxy. Others, just as bright, show no supernova at all. It's a whole zoo of explosive behavior. And that's the fundamental challenge. Can all these different animals come from one family of events? Is there a single physics engine underneath, just operating under different conditions? The search for a unified theory of gamma-ray bursts, that's one of the big pursuits now. It's like the history of understanding stars. A century ago, astronomers had catalogued thousands of stars. All different colors, brightnesses, sizes, a bewildering collection. Then two astronomers, Hertzsprung and Russell, they had a simple idea. They plotted stars on a graph. Temperature on one axis, luminosity on the other, and suddenly the chaos resolved. Most stars fell along a smooth diagonal band, the main sequence. That Hertzsprung-Russell diagram, it didn't just organize stars. It revealed the underlying engine. A star's position was set by its mass and its stage of life. It unified red giants, white dwarfs, main sequence stars like our Sun, into one story of birth, fusion, and death. That's the kind of breakthrough gamma-ray burst researchers are after. A diagram or a set of fundamental parameters that places every burst in its proper place. Where a burst's duration, its energy, its afterglow properties all become predictable outcomes from a few key variables: the mass of the progenitor star, its rotation speed, the strength of its magnetic field, the density of the material around it. So the search is a deep dive into the data, looking for correlations, asking if the energy of a burst is linked to the type of galaxy it comes from. Metal-poor, irregular galaxies, they seem to host the most energetic long bursts. Which fits the massive star model. Short bursts appear in all types of galaxies, even old, elliptical ones where massive stars are long gone, that point squarely to mergers of old stellar remnants. The ultra-long bursts, they might come from stars of a very specific, immense size, where the collapse takes longer to unfold. Or maybe they involve a different kind of central engine. Like a magnetar struggling to form, its birth pangs drawn out over a much longer time. Then there are the puzzles, the bursts that don't play by the rules. The ones without supernova. If a long burst is truly the death cry of a massive star, a supernova should be visible once the glare fades. Yet for some, even with our best telescopes, we see nothing. Does that mean the star completely collapsed into a black hole, swallowing all evidence? Or could some long bursts come from a different mechanism entirely? Maybe the merger of a neutron star with a black hole, an event that might not produce the same radioactive glow. Each anomaly is a clue, a piece of the larger puzzle. And when fitted into place, it reveals a more complete picture of how matter behaves at the brink of a black hole. Achieving this unified model, it would be more than an academic triumph. It would be a leap in predictive power. If we understand the family tree of bursts, if we know that a star with a certain mass, rotation, and environment will produce a burst with specific properties, then we can better survey our galactic neighborhood. We could identify not just which stars might explode, but what kind of explosion they will have and where its energy will be focused. It moves the science from cataloging past events to forecasting cosmic weather. It would tell us with greater precision the true nature of the risk we face, and it would illuminate the final, violent moments of stellar life, as clearly as the Hertzsprung-Russell diagram illuminates a star's long, steady burn. The quest continues, driven by each new flash from the dark, each one a cryptic message waiting to be decoded. That model of stellar death tells us about our own neighborhood. But it makes you think about conversations. If we ever find one, a conversation across the stars would face a universe full of static, not just the quiet hiss of empty space. Sudden, violent bursts of interference. A gamma-ray burst is a brilliant flash across the entire spectrum. For a few seconds, it's the loudest radio transmitter in the cosmos. So picture two civilizations. They've found each other, separated by 1,000 light years. They've started a fragile dialogue, a slow exchange of knowledge beamed across the void using radio or lasers. Their communication needs a clear line of sight, a quiet channel. Then a star dies, not in either of their systems, but somewhere in the vast space between them. And by pure chance, its polar jet is aimed straight down that line of sight. For them, the event isn't a curiosity. It's a catastrophic noise blast. Their carefully crafted signal, carrying maybe years of data, is swamped. Washed out in a flood of gamma rays and X-rays and radio waves, the message is lost, corrupted. The channel goes dark for the duration of the burst and its afterglow. This isn't a dropped call. It's a fundamental challenge for building a galactic network. It introduces cosmic weather, unpredictable, severe storms of electromagnetic noise that can black out interstellar communications for days or weeks. For SETI, the search for extraterrestrial intelligence, this adds a layer of difficulty. We listen for deliberate, patterned signals against the background noise. We assume that if a civilization is broadcasting, its signal will be clear. But what if their broadcasts are intermittent by necessity, not because they turn transmitters on and off, but because the universe itself drowns them out? A civilization might beam a repeating welcome message for centuries, but if a gamma-ray burst erupts along its path to Earth during the tiny window when our telescopes are pointed there, we would hear nothing. We'd log another silent star. This interference could be periodic. If two civilizations lie in a region of active star formation, the rate of massive stellar deaths might be higher. Their attempts to talk could be constantly disrupted, like trying to hold a conversation in a room where fireworks are randomly set off. They might need sophisticated error correction. Sending the same data in multiple bursts, hoping one gets through during a quiet period. Or they might abandon certain frequencies altogether, seeking bands less affected by stellar explosions. This natural scrambling offers another perspective on the Great Silence. The Fermi paradox asks why we see no evidence. One answer might be that the galaxy is not silent, but its conversations are fragmented. Whispered in the brief quiet moments between cosmic storms, Messages may be sent but rarely received intact. Civilizations might be like lighthouses on foggy coasts. Their beams sometimes visible but often obscured by the rolling mist of stellar cataclysms. It suggests a universe where connection is not just about technology and desire. It's about timing and random geometry. To build a lasting dialogue, you might need more than a powerful transmitter. You might need a deep understanding of galactic stellar demographics. Predicting which sightlines are stable for millennia and which are perilously close to potential supernova, it turns the dream of a galactic community into a feat of cosmic civil engineering. Navigating not just space but the volatile life cycles of the stars within it, the universe keeps its history in two ways, in creation and in cataclysm. A massive star collapses, two stellar corpses merge. These events, gamma-ray bursts, are the ultimate cosmic power. They are titans. They can sterilize entire star systems in a flash. But they are also distant forges. They seed galaxies with the elements that make rocky planets possible, that make life possible. We traced their journey. From a classified military anomaly to a cornerstone of modern astrophysics, they might explain ancient mass extinctions. They might influence the great silence of the cosmos. They might shape the long-term survival of intelligence. The probability that Earth ever stares down the barrel of such a beam is vanishingly small. That's a comfort written in geometry. Our quiet galactic suburb, the fortunate timing of our existence, but their presence is a profound reminder. We inhabit a dynamic universe, a beautiful one. And occasionally an unforgiving one. Our pale blue dot, with its thin atmosphere and intricate web of life, is a temporary arrangement of matter in a vast arena where stars live and die by laws of breathtaking violence. This knowledge doesn't have to frighten us. It can ignite a deeper wonder. It fuels our curiosity to keep looking up, to build better telescopes, sharper simulations. It challenges us to think in eons, not years, to consider what kind of future we want to build, one that looks outward with understanding and maybe one day steps outward with resilience. The story of gamma-ray bursts is a story about our own place. In the grand narrative, it's a call to embrace our fragility and our extraordinary capacity to learn, to adapt, to explore.